Log on, tune in, find out. Another good idea from Cambridge.
Ariel from Bar-Ilan University.
Thank you very much for having me here and giving me this opportunity. And this is joint work with Bjorn Enquist and Richard Tsai, who are hopefully will come later this evening. And so before I start with the mathematics, when I was an undergraduate, we were taking physics class, we used to have a joke about how physicists count. The answer being 1 to infinity. Because you do a lot of, you study a lot about one body problem, two body problems, continuum and maybe thermodynamic limits, but in between there's this huge void. Of course there's an immense body of work on three body problems or finite systems, but things are a lot more complicated and there are still a lot of open questions. And it seems like in our business of people involved in multi-scale phenomena or analysis and computation, things are a little bit similar. So there's a lot of work, of course, a non-multi-scale phenomena, system with well-separated timescale. There are a lot of methods that do not assume some kind of a spectral gap, but in between there are still a lot of what I find open and interesting questions. Of course, there are works such as iterated homogenization or averaging methods for long timescales and others, but that's what I want to talk about. This is a conference about highly oscillatory problems, so I want to talk about fast oscillations with three well-separated timescales. So the general setup for what I'll be talking about is just the initial value problem, and we write it in a singular perturbation form. So, but instead of just having the usual two terms, we have another one that involves 1 over epsilon squared. And epsilon, of course, will always denote here a small parameter, and the system, it's not just scalar, it could be in any dimension. And I'll consider finite time intervals, and I will also assume that a solution exists. It is bounded independent of epsilon, and everything is smooth enough. I will not get into issues of how smooth this F should be, and also that the fast dynamics is oscillatory in nature, and I'll be a lot more specific later on. And just a note about the notation. So the subscripts will also always denote to make things clear, will always denote the powers of epsilon that follow. So F2 will be multiplied by 1 over epsilon squared, and so on and so forth. So the goals for this talk are threefold. First, I want to try to understand and define what are the different timescales that are in the problem. Then I'll try to characterize the slow dynamics for oscillatory systems using averaging methods, and finally suggest a computational strategy to compute the slow time observable or the slow time dynamics in the system. So before we go into the three-scale case, I'll shortly review some of the necessary things that we know or some other results that we have for two-scale systems. So I'll go back to the usual case of singular perturbation, ODEs, and here I hope you can recall the talk by Edris that we had yesterday, which really sets the stage for what I'll be talking about. So we have the singular perturbation form for the OTE, and the first thing that we will try to understand, again, Edris talked about this, similar ideas, are what are slow variables. And in here we will say that, say, a variable psi of x, so this is a variable of the original state variable, we say that it is slow if we plug in the trajectory, the solution of the two-scale problem, and differentiate with time, then this will change slowly in time. So things are variable. This can be referred to as a bounded derivative principle, and there is a lot of work about, including also by Kreis. For in this simple example, when we have this separation of f1 and f0, this amounts to see that the gradient of psi has to be perpendicular to the singular parts to f1. So this helps us characterize the slow behavior, the slow variables. You can also look at other observables such as functionals or integrals of the dynamics, but these are all they all have similar nature. So once we have slow variables, we can start collecting different slow variables that we want to approximate, and we don't have to find out all of them. There are, of course, an infinite number of them. It is actually enough to find out if we want to do computations or understand the dynamics. We need to have enough that characterize the entire slow behavior of the system. And to find out what is enough, we define the idea of the notion of a maximal slow chart. So a chart is a coordinate system, and we split it into two types of coordinates, psi0 and psi1. Psi0 will evolve on the 1 time scale, and psi1 will evolve on the epsilon time scale. And we want to find enough, as much as slow variables that we can, enough while this is still a chart, so that the gradient needs to be linearly independent. So we're looking for a coordinate system in which all the psi0s are slow, and the number of them is maximal, as much as we can get. And once we rewrite our problem in these coordinates, then of course the psi0 does not have the 1 over epsilon, and the psi1s are fast. I know this is all very basic, but this is just to get things straightened up, and in order to get to the next three scales problems. So we also need, since we want to do averaging, we will assume that if we fix psi0, so if we fix the slow scale, then whatever we have left, psi1 is oscillatory, and we will assume that is, for simplicity, that it is ergodic on the torus. You can generalize it, but just for now, to keep things simple, we'll just assume that psi1 lives on a torus, and it is ergodic. It does not have to be uniform rotations, though. So the invariant measure on the torus can be complicated. An example for such systems are a perturbed integrable system when you have the separation into action angle variables, and the angle variables live on a torus. There it is simple because actually the angle variables undergo uniform rotations. So the fast dynamics is the singular part is linear, but we do not need to assume that. Later for the computation, we will need to know psi0. Okay, once we have this structure, we have a maximal slow chart, for example, through action angle variables, then we can do do averaging. And I will recall the most basic result about averaging theorem. For example, you can read it off Sanders and Verhulst, and with other generalizations. So we define d mu with this d mu to be the invariant measure for psi1, which is fast, if we fix psi0, and then we look at the average of the, what, does this have a, no. Let's go back. Okay, so we fix the slow variable psi0 and average over psi1 with the invariant measure for psi1, and that gives us the average right-hand side f0 bar. Bar will always denote this kind of averaging, and then we can look at the averaged equation, which involves this capital X. So we just evolve X according to the average part, and using the averaging theorem, one can show that this X, the averaged X, is close to the original psi0 in the sup, with the sup error up to order epsilon. And I wrote this full expression so that we will have it later, because this will be important. So the averaging error here is epsilon times e to the LT, when this L is the Lipschitz constant for capital F. So if we're looking at fixed time, the error is, of course, of order epsilon. And once again, there are generalizations for other types of dynamics other than on a torus. I know. I'm assuming that the initial condition is the same. Yes, you can add boundary layers on top of that, and that adds some other considerations. But for now, I assume that there are no boundary no boundary layers. So we want to do computations. We want to approximate the slow dynamics. So there are many different approaches, and of course that I will not, I do not have the time to survey them all. So I'll just refer you to the to this book on highly oscillatory problems. If I'm not mistaken, this came out of the program 3 years ago. So this is a very nice, has very different reviews, and there are some later additions. So excuse me for anyone who is not covered by these reviews, because I bet that most of the people are sitting here. But what I want to consider, the approach that I want to consider follows the heterogeneous multiscale method, the framework of the HMM framework suggested by and Enquist, and that you heard about earlier this morning. And the idea under this framework is that we want to solve the averaged equation, which usually we do not know. We can prove that it exists, but quite often we do not actually know how to do the averaging, because we do not exactly know we may not know the invariant measure for the fast process. So instead, what we do, we approximate the average, the right-hand side of the average equation, using short time simulations of the full multi-scale system. And we develop these ideas for the two-scale problem on the context of the ODEs in several different previous publications. So schematically, what the scheme looks like is that we are interested in evolving the slow variables. These are the psi zeros that this is represented by the top line. And we have an equation for that. This is the averaged equation. It is close to the full system. And we can do that with macroscopic, with big steps, because there is no epsilon there. However, since we do not know what this average equation is, we do not know what this big F is, we need to approximate it. And to do this, we run very short time simulations of the full system and just do the averaging numerically. If the fast scale is periodic, then we can speed up these averaging if we convolute the solutions or the averages we want to do with a smoothing kernel. This is similar to the modified impulse method when you use kernels to also to get rid of the resonances, but also you can speed up computations this way. With all of this in mind, we can do the full numerical analysis, and we find that if we want a prescribed accuracy delta, and we're using say M0 order method on the 0 time scale and an M1 order method on the epsilon time scale, then we can actually calculate the computational cost. This is in the case where the kernel is smooth enough. So when it is infinitely differentiable. This will be very important shortly, because if we do not use an infinitely differentiable kernel, for example, if we just average naively just by adding and dividing by the number of steps, then this will have a residual power of epsilon here. So the method will not be fully multiscale, in the sense that if we want a fixed accuracy delta, but we take epsilon to 0, then the computational cost will grow with epsilon to some power. But if the kernel is smooth, then the computational cost only involves the accuracy we want, and has no explicit dependence on epsilon. What this also means is that, of course, the time steps that we will take in the micro simulation will be of order epsilon. It has to be of the order of the fast time scale. But the length of the simulation, of the micro simulation, can be taken to be of order epsilon. So the number of microscopic steps does not depend on epsilon. And also the macroscopic steps, nothing are independent of epsilon. So that the overall efficiency depends only on delta. Okay, and we can take delta to be as small as up to order epsilon. Afterwards, it does not make any sense, because this is also the error that we're making by approximating the averaged equation rather than the full one. M0 will be the order of the order of the macroscopic solver, and M1 the order of the microscopic solver. Yes, these are the orders. Thank you. Okay, now for 3 scales. So just to remind you, the 3 goals that we set, first we will try to understand whether the time scales involved for different observable or different variables in the system. Of course, they can be either of the time scale could be either epsilon squared, epsilon, or 1. Then we'll try to find an averaged equation. This will be done by some sort of an iterated averaging. And then we'll talk a little bit about how to do computations using the HMM framework, and I'll finish with a simple example to illustrate these ideas. Okay, so timescales are the first thing that we cannot, just by looking at the timescale at which variables evolve, we can only see that things are not exactly the same as in a 2-scale case. And I wrote down a very simple example to illustrate that. So you can just consider a harmonic oscillator. The leading order, the part that is proportional to 1 over epsilon squared, this blue part, is simply a harmonic oscillator. It doesn't get any simpler than that. And I added some kind of a perturbation. Here, perturbation involves also a 1 over epsilon terms and some terms of order 1. And of course, since this is a linear oscillator, we would want to look at the amplitude or the square amplitude. This is just x1 squared plus x2 squared. And we can just take the derivative with respect to time for I and see what is the ODE for I. And if we just do that, it's just the chain rule, we get 2 over epsilon x1 plus 2i. So since x1 is not always 0, then the square amplitude does not have a bounded derivative. It is not 1 over epsilon squared, but it does have 1 over x. However, it's still a linear equation, non-homogeneous, but we can still do that. We can simply solve it. And if you solve it and plug x1 and x2 to I, you see that it's simply e to the 2t. This makes sense, right, because it's a square amplitude, plus corrections that are actually of order epsilon. So even though the derivative has 1 over epsilon, then you don't see it when you actually look at the amplitude. The reason is that when you average over x1, it comes out epsilon squared. So it doesn't build up to anything. The fact that we have the 1 epsilon here does not matter. So even though I itself does not have a bounded derivative, it is close to a function with a bounded derivative, which is just e to the 2t. And this is, in fact, what we will use to define the time scale for different variables. We will say that a function alpha of x evolves on the epsilon k time scales if we can find a function beta, a different function beta of t, so that beta has k, the derivative of beta looks like 1 over epsilon to the k, and alpha and beta are close. And of course, we will see how far we take it by taking the maximal value of k. So this is how we classify the time scale on which different variables evolve. Once again, we follow the same program. Once we define slow variables, we can look at maximal slow chart. So now we have 3 time scales. So we decompose our variables into psi0, which will work on the 1 time scale, psi1, who will work on the 1 time scale, and psi2, so that each psi, these can be vector valued, evolve on the appropriate time scale, and both first n is maximal and also n plus k are maximal. So we are sure that we are sort of capturing the most slow phenomena as possible. And next we want to do averaging. So let's suppose, again, for simplicity, that psi1 and psi2 all live on a torus. Again, you can generalize that, but I will just consider this place here, this case here, which is simpler. So we are looking for an effective equation for psi0. This is what we're actually interested in. And the first interesting result that we get is that the effective equation for psi0 is always deterministic. that all the averaging error do not add up to stochastic effects, and there are cases in which that do involve three different scales where you see stochastic effect on C0, but you do not see here, and I'll explain it. You never see here if as long as the fastest dynamics is, for example, on a torus, which, for example, means that this is why in Fermi pasta ulam the exchange of the internal energy on the is deterministic and not stochastic on the appropriate time scale. But the averaged equation is not trivial, and I don't want to consider torus, so I'll again become a little bit more specific. This is just for the purpose of presentation. Now I assume that the fastest time scale psi2 is actually periodic, so it lives on the unit circle. Again, this is just to so I can present the averaging result in a simpler way. So the form that we'll consider for the averaging is that we have an equation for psi0 that works on the one time scale, and there's still a singular part, but I am assuming that even though the derivative is not bounded, that psi0 does evolve on the one time scale. And we have a similar equation for psi1. And all these functions f1, f0, g1, and g0, I will assume that they are one periodic in the last variable. And since I put the epsilon to the -2 there, we see that they all oscillate the effect of the... so the fast time scale is really epsilon squared times time. And I just put the periodicity into the functions. And then we have a theorem that we can prove that tells us that the psi0 can be approximated by an iterated averaged equation that simply have the form x dot is equal to some function of x, where this doubly iterated, doubly averaged f has a relatively complicated, or at least a non-trivial functional form that you cannot, you do not just average over the two scale over f1 over f0 to get some kind of a function. It involves f0, you just average over t and psi1, but the effect of f1 is a little bit more complicated as you see it here. I do not want to get into the details here, because what we actually want to do when we do computations is we say that we do not know how to actually calculate the averaged equation. We just need to know that it exists. So we have an averaging theorem with the exact structure, but we will assume that in general we do not know how to calculate it, because we do not know how to calculate the invariant measure, but we do know it exists, and we know that if we are solving the averaged equation, then we are making an O of epsilon mistake compared to the slowest observable psi0. And now we want to take that and use the HMM strategy in a similar way, only now we need to have nested tiers of solvers. So we have three time scales, the one time scales on top, the epsilon time scale, and the epsilon squared time scale. And we want to integrate on the slowest time scale, but whenever we need to take a step to advance the slowest time scale, we need to find the right-hand side. The right-hand side is obtained by averaging over the intermediate time scale. So we need to do an intermediate simulation over the epsilon time scale. But we do not even know the equation on the epsilon time scale. We need to use another averaging to get that. So we approximate each scale by doing a short scale simulation of the scale before. Now this all seems, I think that this seems reasonable, but the question is that it is actually not trivial that this approach holds water. And the reason is that if you recall the standard averaging, the error of the standard averaging error, you can, right, so this was for the two scale case. This is epsilon here, and L was the Lipschitz constant for the average equation. If we look at the fastest scale now, instead of epsilon, we have epsilon squared, and the Lipschitz constant on the intermediate scale is L over epsilon. So we have a big problem here that this exponent diverges very quickly. So the best we can, so if we want to make this scheme work, then we have to be able, so the important requirement is that we can only hope to solve for the intermediate scale for time scale of order epsilon. We can not go any further than that. But fortunately, if you recall what I told you about the two-scale example, if the intermediate scale is periodic, so the intermediate scale is not a torus but really a circle, then we can use kernels to speed up the averaging. And then what as I showed you before, is that all you need to do is solve the of epsilon scale on an of epsilon, on a segment of length of epsilon. So in the periodic case, everything works up consistently, because in order to solve the coarsest, the slowest scale, we need to run the intermediate simulation on a time segment of length epsilon, well, several times epsilon. And this is exactly what we are allowed to do based on the averaging theorem. So for the periodic case, everything works, everything checks okay, and indeed this strategy works. And once again, we can calculate do the numerical analysis and find the cost, giving a fixed prescribed accuracy delta, and there are no epsilons here, so it is fully multi-scale. And in these expressions, again, M0, M1, and M2 are the orders of the integrators on the respective time scale. And this is a complicated, this expression gets complicated. So for example, if you just use Runge-Kutta fourth order method, then you plug in 4, 4, and 4, you get that this is a little bit better than delta to the -1, which is a little bit interesting, because this means that the entire solver behaves as if it was pretty much an order 1 method, because the cost is proportional to 1 over delta. So this is an example, again, just a couple of minutes, a very simple example of two harmonic oscillator perturbed here, but here the red oscillator has a frequency which is slightly different than the blue one by order 1 over epsilon. So if you look at the state variables, this is on the time scale of this is on the epsilon squared time scale. All the variables oscillate with the epsilon scale frequency. But of course, these are harmonic oscillators, so we will look at I1 and I2, which are the squared amplitudes, and theta, which is the relative phase. So you see that on the top one is the epsilon time scale. They are constant, but the phase changes slowly. And then the last figure is on the 1 time scale, when I plot the time evolution of I1 and I2. And these pluses are all these are all sample points that you take with the macro solver. So I did not hide any of them. And this is using Runge-Kutta 4. So again, you see how nicely the macroscopic solver covers follow the correct dynamics, because these are all the sample points that are being used. So no time for future prospects. So I guess I don't need to do that now. So this is it. Thank you.
Okay, let's take time for one or two quick questions, if there are questions.
This method has certain similarities to another method called envelope following. Do you know that method? And they do a short simulation, but rather than using a Runge-Kutta method, they would use a backward Euler method and solve it as a boundary value problem to avoid stability issues with this short simulation. Does that fit into your work?
So so two things. So compared to envelope method, then some of the ideas are similar, because you can, if you look at the envelope method as if you are actually trying to approximate some slow variables, because these envelope methods also sometimes you need to follow the relative phasor. In this respect, this is similar. One of the things that are nice about HMM is that when you follow this scheme, you do not have to follow Runge-Kutta. I just put that so it's because this is the most simplest case. You can use any integrator you fancy on any different scale that can be different, and you can do whatever you need. You can use variables, step size, implicit, explicit. Also, the stability issues are not very strict here, because none of the problems that we're solving are actually stiff, because we're removing the stiffness on each scale. So you can use implicit, but the advantages are not that big. Here.
Okay, I think we better postpone other questions till the coffee break. Let's thank the speaker once again.
Thank you.